Good morning or good evening or whatever it is. BMB 510 MNE 525 class. This is the second part of this week's topic, talking about biochemical kinetics and cellular metabolism. So we talked a lot about the kinetics of DNA denaturation and renaturation. Now we'll go into other types of reactions and how they all fit together to make metabolic pathways and how those are controlled by the organism. So, to precisely calculate a reaction rate without any experiments, we need a detailed analysis of all forces that are involved, all those intermolecular interactions that we talked about from day one. We really need to know all of the things that are going on. Also, we would want to know in a particular reaction what kind of conformational changes are occurring, what kind of rearrangements or relocations of molecules are occurring, to really get a good sense of how rapid things are going to happen. In the absence of any kind of high-powered computer simulation, and I am always in the absence of that, unfortunately, there are some models that we can fall back on. These models have been around for many years, and they're useful tools that can provide us valuable insight into a given chemical reaction, whatever chemical reaction we're interested in. And so first we'll start with the Arrhenius equation. So we think of the equilibrium constant of a reaction and how it can be calculated to be the ratio of two rate constants, and that would be the forward reaction as well as the reverse reaction. So it's the ratio of those two things. And this really only applies to certain reactions. Obviously, the reaction would have to have a forward and a reverse. It would have to, in fact, be reversible. Some reactions, as we've already talked about, are indeed not effectively reversible. But anyway, the temperature dependence of the rate constants must also be similar to the equilibrium, that of the equilibrium constant. And we looked at equilibrium constants earlier, like with the Van 't Hoff equation right here, to get our equilibrium constant. Arrhenius proposed the reaction rate constants should behave in a similar way. So you can see we have similar terms in the Arrhenius equation compared to the Van 't Hoff's equation. We've got an energy term here, activation energy in the Arrhenius equation, RT squared on the denominator here, and we're looking at the change in basically the quantity K, the equilibrium constant for Van 't Hoff, and the reaction rate constant for Arrhenius over time. And so, like I said, EA is the activation energy in the Arrhenius equation. We can integrate that equation to get this, where A is a constant of integration, and then we can rearrange some things here to get the actual Arrhenius equation, which solves for the rate constant. And what you can see from the actual Arrhenius equation is that if you increase A, that's going to lead to increased reaction rate. If you increase the activation energy, that will decrease the reaction rate. And if you think about certainly the last part, that makes sense. If we increase the activation energy, that will ultimately do a job on the reaction rate and decrease it. As we can see here, EA is the energy barrier. The activation energy is the barrier that must be overcome in order for a given chemical reaction to occur. So we can begin to visualize the relationship between activation energy and temperature. Obviously, there's a relationship between these two things. We must begin with the concept of this energy barrier that I just talked about here and is visualized right here. And we can ask what fraction of colliding molecules in a soup of many molecules, what fraction of those molecules have an energy that is greater than the activation energy. We could calculate the distribution of molecules like this, where E, these are the energy, this is energy per mole, or on a molar basis. And so we can take this equation to determine the number of molecules with an energy greater than EA by integrating with respect to the energy from the EA to infinity, or basically anything greater than EA here, and get this equation. And then we can integrate and do some rearranging and get this equation here, where we have a ratio right here. We have that, which gives us a fraction of molecules, and this is the fraction of molecules with the energy that is above the EA. So you can see, of course, the EA term is looming large, and we have our molar fraction here. So the number of molecules that undergo a reaction are the number of molecules that collide multiplied by the fraction of those that have sufficient energy to overcome EA. So two things have to happen, as you know. The molecules have to collide, and if they collide, they must have sufficient energy together to overcome that activation energy barrier that we saw. As a visual, we look at number of molecules versus energy. There is a certain subset of molecules that has energy greater than the activation energy. Okay, so we can apply the Arrhenius equation to molecules colliding. We can also look at Arrhenius equation with respect to enzymes. And again, like we mentioned, there are two ways to increase the reaction rate. We can increase that A, which is an Arrhenius constant, and we can decrease the activation energy. Some enzymes will interact with reactants so as to increase the likelihood of collision in the proper orientation. So that effectively increases that A value. Other enzymes will bind reactants in order to lower that activation energy. And that's why enzymes work the way they work. But some enzymes do both. They increase A, they put those molecules in a proper orientation, and they also lower the activation energy. And that's why in our bodies, in our systems, enzymes are such universal and essential catalysts. Okay, so let's look at an example of this. If we look at a enzyme that is found in enteric bacteria called urease. So during kidney failure, if you have kidney failure, there is a significant amount of urea. Urea is the precursor of what gets excreted as urine, as you well know. But a significant amount of that ends up entering the intestine, which is not where you want it to be. And it is hydrolyzed by bacteria that live there in the intestine using this urease enzyme. And what that does is it cleaves urea to ammonia and carbon dioxide. And this is not a balanced reaction. So save the emails, please. Anyway, if we have a non-enzymatic reaction of urea hydrolysis, the activation energy is around 30 kilocalorie per mole. But however, if we're looking at a urease catalyzed reaction, an enzymatic reaction, in other words, that activation energy drops from 30 to 11 kilocalories per mole. And we can see by this simple ratio of the rate constants how that affects the rate of the overall urea hydrolysis reaction when we're looking at enzyme versus no enzyme. And so if we take a ratio of the rate constant with enzyme over the rate constant with no enzyme, we get a value of 1.5 times 10 to the 14th. So we can plainly see here, and it's striking when you look at it, that the enzyme increases the reaction rate constant, thus increases the rate by 10 to the 14th. And that's incredibly huge. Incredibly huge. How would we even begin to fathom getting that kind of an increase in rate without the enzyme? Well, to do that, hypothetically, of course, the same reaction rate without enzyme, according to Arrhenius' law, we would have to run that reaction at a temperature of 529 degrees Celsius to get that same magnitude of rate constant compared to the rate constant with the enzymatic process. And so kind of the segue for that is that we can run with that theoretical increased temperature, but we're increasing the energy of everything, not just urea here. The advantage of enzymes is that they can be selective depending on their particular substrate. So in the urease case, like we said, not every reaction rate is going to increase by 10 to the 14th if we use the urease enzyme. Whereas if we were increasing that temperature, then we're increasing every reaction rate in the cell, hypothetically. We all, of course, know that the cells wouldn't be able to survive that kind of high temperature anyway. And so you can see what being selective means here by this little cartoon that looks at alpha amylase, the protein, the enzyme that cleaves the glucoses in starch. Where if we have alpha 1,4 linked glucose, the certain linkage that holds the glucoses together, or starch as it's called, alpha amylase fits nicely in here, and the starch fits in the active site, and a glucose will get cleaved. However, if the polysaccharide is beta 1,4 linked, you can see that, well, this enzyme is selective, so this alpha amylase is not interested in cleaving a beta 1,4 linkage in glucose. In other words, it's not interested in breaking down cellulose. It just can't. It's the wrong conformation. So that's what we mean by enzyme selectivity. Okay, and especially if we think about organic molecules reacting and forming new products, we can think about what role entropy has to play. And there is this theoretical model of reaction rates that includes entropy effects, known as the transition state theory. And when we think about transition states, we can often think about organic molecules. Basically, the concept is this: reaction rate depends only on the concentration of high energy activated complex. You can see down below here we have this nucleophilic substitution reaction that's going on, this hypothetical one. We have a high energy transition state complex right here. And so this complex is only weakly bound together. And therefore, with this high energy complex, the reaction can go in one of two ways. It can either progress forward to make our product, or it can just reverse itself, go backwards, and end up as the two reactants again. It'll go back to the way things were. So it's either going to go in the forward direction or the reverse direction. And the transition state theory takes into account the entropy effects that kind of deal with that idea. Okay, so say we had again a hypothetical equation, A plus B yields C. What would that look like using our transition state theory? So what we would have is A plus B yields in a reversible manner this high energy activated AB star complex. The AB star complex is in equilibrium with A plus B, our two reactants. And so we would have a equilibrium constant that looks like this. And from this we can calculate the free energy of formation for the high energy complex AB star. So we get our K star, and we plug it in here, and we can end up with our delta G for this complex. So the weakness of the bond in the AB star complex means there's two possibilities. Either AB star is going to dissociate back to A plus B, our two reactants, or it will complete the reaction to form C, the product. These possibilities will occur as a result of any kind of molecular vibration that goes on. And so it'll nudge it, that kind of vibration will nudge it one way or the other. And the reaction rate is thus equal to the vibrational frequency. So when they vibrate, the molecules or the high energy intermediate will react either going forward to make product or going backward. So quantum physics says that energy is equal to h times the nu here, the vibration. So h is Planck's constant. Classical physics tells us the amount of molecular vibrational energy is related to temperature. In this equation here, E equals 3/2 kB times T, where kB is our Boltzmann constant. So we can combine these two equations to look like this. And then we can use that right here for our transition state equation here. We can look at the reverse reaction, where k to the negative 1 is equal to kB times T divided by h. So we get two constants in there in temperature. Note that we got rid of the 3/2 since this is an approximate method. No one's going to come after us on that. The forward reaction, K2, is equal to kBTH as well. So if we do our mass balance here, our change in concentration of C over the change in time is equal to K2, the forward constant, multiplied by AB, the concentration of AB star, which is also equal to K2 times the equilibrium constant for A plus B and AB star, multiplied by A and B, concentrations of A, and multiplied by the concentrations of B. So we can see we have K2 times K star is equal to this K, this reaction constant, this reaction rate constant for the equation. And remember our equilibrium constant equation right here. We can combine these things and get what is known as the Eyring's equation, which looks like this. This is our rate constant, including our vibrational energy term, along with the delta G terms. Delta G star is our energy of activation, where AB star forms product. Okay, so it should be said that transition state theory is more accurate than the Arrhenius equation, even though the two equations themselves have a similar form, as you saw. The transition state theory, however, includes an entropy term, and you can see why that might be necessary based on what the transition state is all about. And anyway, we have the classic free energy equation here, which we've grown to know and love over the years. If we combine that with the Eyring's equation from the last slide, we can use the below equation here to get our delta S. And so some last thoughts on this. You will note that the Arrhenius theory says that the delta H, the change in enthalpy, is equal to the activation energy minus RT, suggesting that EA depends on enthalpy, not entropy. Gibbs free energy of formation of the high energy activated complexes. Delta H is always positive. It's endothermic, energy absorbing, because bonds must be broken in order to reach the activated state. Delta S could be positive, could be negative, depending on the allowable configurations for the specific reaction, for the specific transition state involved. What does this tell us in all actuality about enzymes themselves? They can decrease delta H, the enthalpy, by helping to break bonds. That to a degree tells us about their ability to position substrates in the right manner, and they can increase delta S by providing more high energy configurations for the molecules. Again, talking about those configurations. So enzymes can do these things. They can decrease the energy, as we already know, and they can increase the entropy. And this is how they help This is how they help get chemical reactions done. Okay, so let's move on. The transition state theory isn't good for every reaction, as I mentioned. Imagine a reaction that is so favorable that every time reactant molecules collide, that reaction occurs. You end up getting products, such as the high energy intermediate being immediately consumed for product formation. Doesn't have time to think about going back to becoming reactants. So in a case like that, the transition state theory is not going to be as helpful because we're not really in a transition state for very long, if at all. A inquantifiable amount of time, a small amount of time. These are known as diffusion limited reactions. So the diffusion limited model assumes that a reaction occurs every time two molecules get within a certain distance of each other. That distance can be denoted R12, and this is called the reaction radius. Molecules in solution, whether that solution be a beaker, a test tube, a bacterial cell, a human cell, they move by Brownian motion. So they just kind of stumble around in our cells and other places. So the rate of motion is governed by a diffusion process. And diffusivity constants are needed. dA if we're talking about reactant A, and dB for reactant B. So those will be needed, as you can imagine, since we're talking about diffusion limited reactions. Those will be needed to calculate our rate constant. And we can see that equation right here, where K is equal to 4 pi A multiplied by dA plus dB times R12 divided by 1,000. A, incidentally, is not the Arrhenius constant, just to confuse you. A in this case is Avogadro's number. Sometimes, when we're talking about diffusion limited reactions, we might want to consider reactants with a charge. For this, we get a Debye parameter here, which is this phi, the ratio of electrostatic energy of particles and their thermal energy. There are several new terms here. Za is the charge of particle A, Zb is the charge of particle B. This EPS term is the dielectric constant, and Kb is our Boltzmann constant. You know T as temperature. And so with this parameter, we can rewrite the equation for K to look like this if we're talking about diffusion limited reactions with charged particles as reactants. Okay, let's move fully into enzyme catalyzed reactions. Let's go from the micro to the macro for real here. Most reactions in the body, like I mentioned, are catalyzed by enzymes. Controlling enzyme activities in our bodies or in any organism is a critical mechanism. And so we need to adapt our metabolism to any changes in the environment. And a good example of that is glycolysis gluconeogenesis. And so depending on whether you're hungry, not hungry, just eaten, that sort of thing, you need to control this stuff. So control is achieved in glycolysis or gluconeogenesis by reciprocal regulation of two enzymes. This fructose 1,6-bisphosphatase and 6-phosphofructokinase. These two enzymes right here, and you can see the schematic of what they do right here. They interchange from fructose 6-phosphate to fructose 1,6-bisphosphate. And you go one direction, we're going through glycolysis. We go the other direction, we're going to gluconeogenesis. And so, again, we talk about the necessity of molecular interactions. A good example of that is forming an enzyme-substrate complex. So there has to be molecular interactions with the enzyme-substrate complex. A good example of this is the chymotrypsin here. And you can see this is a mechanism slide of chymotrypsin where we get the peptide bonding here, and we get interactions that occur between amino acids in the enzyme and the substrate, and we get a intermediate. We get some high energy intermediates here, and then we eventually get cleavage We get cleavage, we lose one product, we still have this intermediate. We restore the side chains of the amino acids finally, and then we remove the other product here by this enzyme substrate complex is then able to release both the products here. The rate of reactions that are enzyme catalyzed is a function of reactant concentrations. At low concentrations of substrate, the reaction rate is a linear function of substrate concentration here. And the reaction is first order with respect to substrate when we're talking about these low substrate concentrations, as you can see here. But after we increase the substrate concentration significantly, like up on this part of the curve, the reaction order tends towards zero order. So the presence of reaction, the reactants is enough. Zero order, we've got maximal rate, regardless of whether we add or take away a little bit of substrate here. We're first order initially as we're filling up the active sites, but then after a while our active sites are overfull of our enzymes. Okay, so here you've probably seen this before, where we have enzyme plus substrate yields the enzyme-substrate complex, and then at a certain rate we get free enzyme plus product at the end. But also at a certain rate we get enzyme-substrate complex dissociating to enzyme and substrate again. The mechanism assumes that the first step is reversible. So enzyme-substrate complex going to enzyme plus substrate, that's reversible. And it assumes that enzyme plus product is an irreversible thing. So the overall reaction velocity is this dP dt, the change in product concentration over time, is equal to that K2 rate constant times the concentration of enzyme-substrate complex. We can also do mass balances for substrate and enzyme-substrate complex, and they look like this, where we have negative ds dt is equal to K1 multiplied by substrate concentration and enzyme concentration minus K to the negative 1 times the concentration of enzyme-substrate complex. The change in enzyme-substrate complex is very similar here. We have K1 times substrate times enzyme, but we can, when we're talking about the loss of enzyme-substrate complex, we can add up the two rate constants that basically dissociate the enzyme-substrate complex, either as enzyme plus product or enzyme plus substrate again, and how we have this term here. And since all enzyme present in this reaction is either going to be free, that is without substrate, or it's going to be complex with substrate, we can easily make a mass balance of enzyme, strictly enzyme, where a total concentration of enzyme is equal to the amount of enzyme-substrate complex plus the amount of free enzyme here. And you can see over the course of a reaction, this will change slightly, though, in terms of the total enzyme and total free enzyme and enzyme substrate complex. So for this stylized graph, we see the amount of substrates decreasing, the amount of product is increasing, and this should be free enzyme, not total enzyme here, where we have the amount of free enzyme decreasing as the amount of substrate enzyme substrate complex increases here. Okay, so you could kind of see that once we get a certain amount of enzyme substrate complex, the concentration seems to stay relatively constant throughout the reaction. That, in other words, the change in the enzyme substrate complex concentration over time is approximately equal to 0. So that's how we can write our enzyme-substrate complex mass balance that we introduced earlier. And then we can move around the mass balance for substrate to look like this. Negative dsdt is equal to the K2 times total enzyme concentration times substrate plus our divided by our gamish here of a rate constants plus substrate concentration. And so we can sort of see what this is going to end up, what this equation is going to end up becoming in. It's a very familiar one. So we can take that mass balance and rewrite it like this, where the reaction velocity is equal to the change in substrate concentration over the negative change in substrate concentration over time. And we can give these other things new names. K2 times the concentration of enzyme is called Vmax. The substrate concentration terms stay the same. This rate constant term is given the name Km, as you can see here. So Vmax represents the maximum reaction rate in an enzyme reaction when all active sites of the enzyme are occupied. And we can visualize Vmax in this way, where we have reaction rate versus substrate concentration, where we don't, in the what we call the first order region here, we don't have full active sites of the enzyme, but as we move towards the what we call the zero order region here, up where there's a lot of substrate for the enzyme is saturated. It's got far more substrate than it can deal with, so the active sites are always full. This is our Vmax here, that maximum velocity when the enzyme has so much substrate that it's always full. So we can rewrite this equation, this rate equation, like this in a reciprocal fashion, and then plot that. So instead of getting a curved line like that, we end up getting straight lines. We get the plot of 1 over V versus 1 over substrate concentration, giving us a straight line. And we can get some good information out of that. We can get, with our slope, we can get the Km divided by the Vmax. And with our intercept, we can get 1 over Vmax. This type of plot is the Lineweaver-Burk plot. You can see an example of that here. Again, we're looking at 1 over reaction velocity divided by or versus 1 over the substrate concentration. Here's our slope that would give us Km over Vmax. Our y-intercept right here is 1 over Vmax. We can interpolate or extrapolate down here and get a negative value here, which is essentially the x-intercept is our negative 1 divided by Km. And so we've thought about enzymatic reactions that have one kind of enzyme-substrate complex, typically one enzyme, one substrate, but many reactions involve 2 substrates instead of 1. So for example, if we're looking at a dehydrogenase reaction, if we're looking at a reduction reaction, these reactions involve a cofactor like NADH, NAD, NADPH, NADP, things like that. So we have 2 substrates, and we have a little more complex enzyme-substrate complex formation thing to worry about here. And so they follow the general scheme here, where we form one enzyme-substrate complex, we form another, and then eventually, when we have this enzyme-substrate 1, substrate 2 complex, we go towards the product formation and the release of product from the enzyme. And so our rate is basically dictated by the K3 rate constant times the concentration of this enzyme substrate 1 substrate 2 complex. Okay, so we'll talk just a bit about multi-enzyme systems. That is code for metabolic pathways. So here's a simple 2-step pathway where we have a substrate and one enzymatic reaction converts it to an intermediate. and that intermediate is not like the high energy intermediates we talked about earlier. It is any given intermediate compound that is more or less probably stable on its own, but it is the product of this enzyme 1, but the pathway is not done with it yet. The enzyme 2 is going to take that intermediate and convert it to the metabolic pathway product. So we have two enzymes. Substrate is taking the product through one intermediate. So if we think about the net rate from substrate to product, that is given by a variable called J. That's the net rate from here to here. And we should note that the velocity 1, or the velocity of enzyme 1, equals the velocity of enzyme 2, equals that J, that net rate, that net flux. And if this is in steady state, if the pathway is in equilibrium, this is uniquely determined by the parameters of the system. So it depends on what enzyme 1 and enzyme 2 are. And we think about the levels of the activities, and then of course there's also we have to take into account the concentrations of substrate and product here. So steady state entails determination of the intermediate metabolite concentration. So how much of this do we have, along with the pathway flux, or that overall rate J. If we change something, say the enzyme 1 activity increases, we'll get a new steady state, which will be characterized by new values for the given variable. So we'll talk more about what constitutes a variable in just a second. Substrate and product concentrations, enzyme activity, these are all system parameters. These are parameters of our given system. What is going to change, more likely than not, are these variables. The intermediate concentration, so that concentration of I there, and the total flux through the pathway. These are variables. So basically, if we change the enzyme activity to E1, we will see new values for the total flux through the pathway, new values for that concentration of intermediate, which kind of makes sense. Okay, so we can visualize this, or we can begin to understand this by using flux control coefficients. These are determined by the relative change in a steady state flux divided by the relative change of an enzyme activity. That is the dry version. A perhaps more understandable version might be the change in flux is being caused by change in enzyme activity. That's typically how it's going to be. And because enzyme activity is an independent system parameter, it's not a variable, remember, its change will affect flux both directly and indirectly. So directly through its own change, and indirectly through changes imparted on other system variables. So we have a flux control coefficient. Because they are defined as terms of relative flux and activity values, they don't have any dimensions. So we're not talking moles per hour or anything like that. They're dimensionless numbers. Their magnitude is independent of the flux and activity units that are used. For a linear pathway, which all we're going to talk about today is a linear pathway, flux control coefficients have values that range anywhere between 0 and 1. There is a school of thought called the Summation theorem, and that means that the sum of all flux control coefficients of a pathway, for all enzymes in a pathway, on that flux J, the sum of all these is equal to 1. So what does that mean? So we have our small pathway here. So for this simple pathway, we have two enzymes and therefore two flux control coefficients. According to the summation theorem, the flux control coefficient for enzyme 1 plus the flux control coefficient for enzyme 2 is going to equal 1. And no changes affect the system. How much? That is told to us by elasticity coefficients. Control coefficients are systemic properties of the overall metabolic system. Elasticity is a local property. So we've got a systemic property, the control coefficient. Elasticity coefficient is our local property. Most common is the sensitivity of reaction rate with respect to metabolite concentration. Elasticity coefficients can be regarded as an apparent reaction rate order. So remember, as we said, the lower concentration of substrate, we are in an apparent first order reaction, whereas in very high substrate concentration, we are in an apparent zero order reaction situation. So that's essentially elasticity coefficient talk right there. Positive values for elasticity coefficient indicate metabolites stimulate a reaction. Negative values indicate metabolites slow a reaction. And so the elasticity of whatever reaction rate, the ith reaction rate, with respect to the concentration of the metabolite, X, is defined as the ratio of the relative change brought about by a change in metabolite concentration. So how that metabolite concentration change affects activity. And we're assuming all other system variables did not change from their steady state values. And so we have the connectivity theorem. We talked about the summation theorem. This is the connectivity theorem. We have two enzymes, therefore two flux control coefficients in this scenario here. We also have two elasticity coefficients. According to the connectivity theorem, the flux control coefficient for enzyme 1 multiplied by the elasticity coefficient of metabolite 1 is plus the control coefficient of enzyme 2 multiplied by the elasticity coefficient of the metabolite 2 is equal to 0. And we can show that visually, and hopefully it makes a little more sense here. So enzymes with low elasticity exert a strong control on the overall flux. So to the left, we look at the elasticity of enzyme 2. We are inhibiting enzyme 2 here in this little pathway. The elasticity of enzyme 2 with respect to the intermediate concentration is greater than that of enzyme 1. So we hit it with we inhibit the reaction by putting in a chemical inhibitor, let's say, for enzyme 2. We see a drop in the velocity of the reaction, which eventually builds back up to normal here. And we can see that with the elasticity of enzyme 2 being greater, it's not exerting as strong a control on flux here. You know, velocity, the first velocity is just kind of moving along. And we inhibited enzyme 2. It was inhibited for a while. We built up a little intermediate. But now, towards the end here, the velocities of both are basically back to normal, back where we might expect them to be. So that's the hallmark of a larger elasticity coefficient. Enzyme 2, on the other hand, the elasticity on this side, the right-hand side, is much less. And you can see we inhibit it. It goes low in terms of velocity and stays low. And the velocity of enzyme 1 follows suit. So the inhibition of enzyme 2 is a much, much greater effect on the overall flux and on the different enzyme activities in this scenario than it has in this scenario. And that's because, what tells us this is that the elasticity of enzyme 2 is greater than that of enzyme 1. Over here, it tells us the elasticity of enzyme 2 is, this is greater than enzyme 1. This is less than enzyme 1. So again, enzymes with low elasticity, like the case here for enzyme 2, is exerting a strong control, and you can see that strong control on the flux and the way the graph is shaped here. Okay, so that's it for this one. I will hopefully be posting assignment within the next day or so. I apologize that everything is so far behind. I did not intend for this to be the case, but it's kind of how it worked out. but fear not. Just keep working on assignment 2. Ask questions if you need to. And assignment 3 will be forthcoming. The deadline for that will be reasonable, I can assure you. And we will hopefully meet on Tuesday and talk about fluid dynamics. Thank you.